I'm an educator. I will teach you the causes and effects of what science, knowing what science is and how and why it works.
Which is why it's critical that you continue to criticize science fiction movies. It's very important. Don't you back off now. We need you. There's a lot of people that wouldn't know that Chinese space station is nowhere near the American space station, and that her hair would be moving all over the place.
Her hair would be everywhere. Yeah. Oh, now, but my favorite one is, remember when he's at the end of a tether? And she wants to save him, but she doesn't have enough oxygen to do it. So he lets go of the tether, and that way she can't save him. Therefore, she can save herself.
Right.
And then he flies away. It's like, no, they're like floating in space.
Yeah.
He lets go of the tether; it just stays there in his hand.
Yeah.
Doesn't.
He would be right there.
He would be right there. Nothing. He lets go. Nothing happens.
Wouldn't be like a bungee cord.
Now, if she were swinging him in circles, and he let go, yeah, he'd fly off at a tangent. But that's not what was happening.
Right.
And nor were they rotating. I would check what they were relative to Earth below. That was not what was going on. So, and you know what? She could have just given it a slight tug, and then he would have drifted towards her. That could have even been a little romantic.
Just a little baby tug.
Yeah, baby tug would do it. They would slowly drift towards one another.
No, I hate
and
that movie.
Then the helmets would hit, and then
that movie makes me mad. Oh, and then the helmets would break, and then they would be freezing to death instantly, right? When you just freeze,
you'd suffocate.
Oh,
first.
that too, and then freeze to death, right? What movie nailed that? There was one movie where they were off in space. They overdid it.
Well, there was. People want you to like explode in space.
Yeah.
No. I mean.
Well, they want you to freeze solid too instantly.
Yeah, right. No, just no. And even in, was it Armageddon, where the sun rose over the comet, and he didn't have his visor down, and he was blinded by the sun. It's like the same sun in our daytime sky.
The atmosphere doesn't protect you in any way?
The Earth's atmosphere takes out, a few percent.
That's it?
Oh, yeah.
Oh, God.
A few percent. Well, in the middle of broad daylight at the top of the sky.
So you just be
squinty. It's a few percent. Now, he'll get more UV. He'll get more UV. That's important.
Get a little more brown.
Yeah, but... death in space is nowhere near as spectacular as movies would have you think.
Yeah, they make it seem like if you take that helmet off, you just immediately freeze up.
Yeah. No. I mean, you can go into what happens is there's nothing making you cold other than you radiating heat from your skin.
Oh.
So you'll only get as cold as quickly as you can radiate away heat. That's all.
So it would take quite a while.
Oh, yeah.
You just have no air, so you'd suffocate quicker.
Yeah, you'd suffocate. Oh, yeah, you'd suffocate long before you saw anything like that happen. So just think about it. There's nothing touching you that's making you cold. It has to wait for you to radiate away. That's what's happening, okay? And you'll feel very cold very quickly, but you're not going to die from that fast.
Now, when Stephen Hawking...
Oh, by the way, you also have dissolved gases in your body, which will try to come... Because in the vacuum of space, you don't have the air pressure tamping down the dissolved gases. So you take away the air pressure, then the dissolved gases will begin to bubble out of your blood. Oh. And it's the same problem with when you have the bends.
Oh.
When you come up from low altitude and you go to lesser pressure
you get
around
nitrogen poisoning.
Yeah, you get nitrogen. So you want to do that slowly so that it's a very slow thing. But the hazards of... But then why would you be butt naked in space? I mean, you're going to have a spacesuit on. So.
Well, you just want to prove to everybody that you could do it. So,
well, they did it
Jackass.
in 2001 at Space Odyssey. They basically did it right. The guy, without his helmet, went through the airlock. And he just held his breath.
Oh, okay.
Yeah, that's all he did.
Oh, well, that's way more reasonable.
Well, because it was a reasonable movie.
It was a reasonable movie. It was a good movie.
It had real advisors.
Stanley Kubrick. Well, he was a really interesting guy, too, because he was a mathematician. Stanley Kubrick.
I didn't know that about him, but I knew he cared about that level of detail.
He used to do complex math for fun.
So there's a failed bit of physics in 2001. You want to hear it?
Oh, yeah.
Yeah? One day I'll talk about
the
2001.
Monkey suits?
No, so...
The monolith? Which was it?
No. So remember when he's on one of the moon crafts and he's orbiting the moon and they give him food. All right, and there's a tray of nasty food, obviously. It's like astronaut food. Remember, this is 1968, so everything here is a visual taste of the future. So he has another packet where he extends a straw from that plastic packet. Okay? Oh, there he is. Excellent. You're getting the good photo. You're good. Your boy is good right here. Okay? Yeah, there he is. So he sucks up the straw.
Right.
And this is in zero G, so stuff is floating around. He sucks up the straw. Then he goes to another straw, and the liquid in the straw goes back down That's gravity.
Oh, they fucked up.
Yeah.
Oh.
He totally fucked up. No. No, so that one, obviously, he can't get everything right. But it's fun to notice the things he couldn't get right or didn't think to get right. So to me, it's a celebration. Here's another one.
Okay.
The rotation rate of the space station. I calculated that, and I calculated what G-force would you have on the outer perimeter of the space station in 2001. And I did the math, and I forgot the exact number, something like between 2 and 3 Gs.
Oh.
And I said, why would you do that? That's stupid. You wouldn't do that. And I realized if they rotated it at the rate that would give you 1 G, it would be way too slow to make an interesting scene. So I gave it to him. I said, I'll give you 3 Gs. Because the Strauss waltz, as the thing turns, and the space shuttle that's approaching it matches its rotation rate with the opening in the center of the space station. This whole ballet, this entire ballet...
Wow, that's cool looking.
Happens at a stately but real pace. Okay? But that pace gives him a 3 Gs of gravity.
So it's 3x the correct pace. The correct pace would be
It's
much
3 times.
slower.
Yeah, it might have been 2.5, but I forgot the number. But it's multiples too high.
So
but
that is
it looks
possible?
good. And so I let him do it. I'm not going to. I'm fine. That's artistic license. That's Mark Twainian license, where he says, first get your facts straight, then distort them at your leisure. That is what I'm holding artists to.
So now, when you're looking at a space station, like they're in zero gravity when they're in the space station.
No, they are in 1 G on the edge of the space station.
On the edge?
Yeah, on the turning edge. Yeah, that's the whole point.
You mean that thing?
So
I mean
so
a real space station.
If the thing, our space station.
Yes.
Oh. So it's 0 G. Yes.
Right now, but it is possible.
It's 0 G because it is in free fall towards Earth.
So it's constantly in free fall, but it's just going around the...
Yeah, it's in free fall towards Earth, but it's going sideways so fast that the amount that it has fallen equals precisely...
the spin of the Earth.
The curvature of the Earth.
Is that more proof that the Earth is round? Is it?
If you've had Physics 101, yes.
But is it possible to generate gravity in a space station?
Only if you rotate it.
Only if you rotate it.
It's not gravity, it's you're simulating gravity. But according to Einstein, they're indistinguishable from one another, so you can do it.
So it is possible to do something where you can send people into deep space and generate gravity through some sort of rotation?
At least 2 ways. One of them, you just rotate it. And all the good sci-fi movies have rotating sections of a space station.
Right.
Right. And there's some that have rotating opposite ways so that they can spin up against one another. Right. And so there's some clever ideas out there with space stations of the future for long voyages. Because
I had Commander Hatfield on the podcast.
Cool.
Who came back from space and was talking about the excruciating difficulty he had readjusting to gravity after being in a zero gravity environment for so long.
He's just showing off because he's like setting records for being.
Wasn't he like 6 months?
Yeah, it was a long time. He's showing. Yeah, I couldn't handle life with you lowly Earth people.
He was talking about his body. Like it took like over a year before his bone density came back. And
this is partly addressed in the film the Martian kid. He's born on Mars, comes to Earth.
Which one's that? Born on Mars.
Yeah, the kid born on Mars. Get your guy to research this like now. What's the name of the movie? It's
recent.
Yeah. Oh, the Space Between Us.
Oh, what the hell's that?
You got to get out more, dude.
I do.
Yeah.
But that's
so
this
is a Martian colony where the first community.
What movie is this?
This came out a couple of months ago.
Really?
Oh my gosh! Oh yeah.
Oh man, I'm so behind. Is this out on iTunes yet?
So that's the Martian colony, and one of the female astronauts they send, that one there, happens to be. They learn is pregnant, and they can't bring her back, and so she gives birth on Mars, and the first person who is ever born on Mars. And then they keep it a secret, and then he comes back as a teenager that falls in love. See, there's the fetus. So anyhow, he has a hard time on Earth because his heart developed in Martian gravity, which is only 38% Earth gravity.
Oh wow!
And then on Earth, he just couldn't. They had to, figure out what to do with him.
Wow.
Yeah, that's on Mars. The kid was born on Mars.
Okay.
Yeah.
Don't spoiler alert me, Jamie.
Yeah.
Shut that off.
That's why. Yeah. So. Where were we talking
Generating
about?
gravity in
so one way is to
travel.
rotate it up. Another way is if you're headed somewhere,
right?
You
Like
just
Mars.
have a huge fuel tank and just always run your rockets.
Oh,
Then
so you always
just
have
accelerate it.
G-force.
There's always a G-force.
Oh,
so if you
interesting.
accelerate at 1G
Right.
towards a destination, then you'll
You'll
always
always have
feel
1G.
Earth gravity, and you'll get there awesomely fast.
But you would have to have so much fuel or
Yes, you'll
rely
need
on something
well, you
new.
need filling stations en route, this sort of thing. And if you do this, you accelerate 1G halfway there, then you turn the spaceship around, then you decelerate at 1G for the other half of the trip, so that when you get there, you're not whizzing past it in a flyby. Okay? That way you have 1G the whole trip. That's how you would do that.
Wow. So the momentum when you would precisely hit
If you accelerate
halfway
it
there.
at 1G, oh my gosh, you hit near the speed of light very quickly.
Whoa.
Oh my! I mean, I forgot what is it in a. I have to calculate it, but it's the acceleration of Earth's gravity. If you actually move that fast, that's head snapping.
Now, would they have to have some sort of a crazy propulsion system in order to do something along those lines? How fast will 1G get you there? 1 year.
Yeah. So yes. So
Wow.
1G would take
1 year plus the distance in light years. Proxima Centauri 4.2 light years, for example, would take 5.2 years. So the distance in light years plus a year. Wow,
Yes,
that's
accelerated
crazy.
1G. So that's so that gets you basically 25% the speed of light.
But what happens if you just run into stuff on the way? Like,
That's
there's a lot
bad.
of stuff out there, right?
Yeah,
I mean,
so
isn't that a giant issue in getting to Mars?
Well,
all the
space
stuff?
is actually quite empty, but if you do hit something, that's the end of everything. So it's a low risk, high consequence thing that
Right.
you gotta put in play.
Now, how much of a risk is the space junk that we've left in the environment?
Oh,
'Cause
don't get me started.
We were
Oh.
freaking out the
Oh,
other
we
day
got
about
so-
how many
we got
pieces
s-
are up there.
We got there's countless thousands of bits of space junk.
Yeah.
From chips of paint that fell off of
To
space
bolts.
to bolts and nails and
Retro rocket boosters and-
Yeah, it's all up there, and I'm wondering whether we haven't been visited by aliens yet because they saw the space junk orbiting Earth and said, "Forget that. I'm going to visit some other planet. I'm not going to risk my life."
Crazy short-sighted approach to space travel.
Yeah,
to
so if you
litter
bring
our-
up the NASA Orbital Debris Office website, you can actually see the debris that NASA's tracking, almost in real time.
It's crazy
They'll
how
show
much
it to you.
there is.
And it's like a beehive around the Earth. So you got there it is. Okay, that's the debris around the Earth that NASA tracks.
And there's a failed Japanese experiment to try to...
And that outer ring that you see, that's the altitude of geosynchronous satellites, and that inner. Now, there should be a video of that. Just fine. Yeah, go to the bottom right. Go to bottom right, right there. Click on that. Play that video. It's not a video. Why isn't that a video?
I'm sure there is a video somewhere.
Yeah, there's a video
He'll
on that
find
site.
it.
So you can just see the movement of these pieces, and so launch windows have to know when to not hit stuff. So,
jeez.
so when you have launch windows, it's not just is everything aligned right, will you successfully get past the debris?
And there was a Japanese, they had an experiment to try to capture it with nets. It was a recent mission.
Oh, yeah. So
Didn't work.
Yeah, so the problem is the low orbit stuff will eventually fall in and burn up. The high Earth orbit stuff will never go away. There's nothing to destroy it.
And so they can't capture that stuff?
Well, you need a very clever. This stuff is moving 18,000 miles an hour. So what's your net? What are you doing?
That's so crazy.
Oh yeah, there you go.
There's the video. Oh
Yeah.
my god.
Go higher res on that. Sure, I know there's a higher res.
God.
That's 1080.
Well,
No, it's not.
it's not from NASA's YouTube panel. It's from
Oh,
some other-
okay, somebody else. But that's the kind of, so all of that's debris that you're looking at there. So anyway, yeah, so your concern for debris is well placed. And we may be putting so much debris in space that we will close ourselves off from space travel because of the dangers it would take to get through our own garbage heap.
That's so crazy. And this was all started in the 1940s. 1950s? Like, when did they start shooting stuff up there?
Oh, no, 1950, Sputnik. Yeah, 1957.
That was the first satellite, right?
First anything, yeah, first anything in orbit. Yeah.
Oh, God. And in that short amount of time.
Yeah.
That's
yeah.
crazy.
Yeah, it's like a dumpster.
60 years.
Planetary
They
dumpster.
ruined the whole thing.
Ruined the whole thing.
They've had it for billions of years. In 60 years, they filled it up with junk.
Yep.
That's
okay,
just
there it is. Yeah.
Oh my God, that's
See
terrifying.
that? Yeah, that's going around the Earth.
Oh my God.
All of that.
Oh my God. And has anybody ever hit anything while trying to do something?
What exacerbates it is, remember when China, when was this? 2004, 2003? China destroyed one of its own satellites.
Yeah, what was that
upper
about?
orbit.
I remember some of that.
Yeah. And they basically did a kinetic kill on a satellite. So a kinetic kill, for those who don't know, is you don't need explosives if the speed of the projectile and its kinetic energy is higher than the energy that would be in the explosive shell itself.
Oh.
So it's a fascinating calculation to make. So here it is. So I have this delivery system with a warhead, and I put some bomb device in the warhead, and you can calculate how much energy that is. Then I send it, and it hits, and it blows something up. But suppose I send this thing really, really fast. Really, really, really fast. I can calculate how much kinetic energy this thing has. There will be a point where I give it so much kinetic energy, the kinetic energy is greater than the chemical energy of the conventional explosive that I put in the warhead.
Oh, like Shoemaker Levy.
Well, no. Well, for example.
Yeah.
I give you a terrestrial example. You ready?
Okay.
It's what we call a high-speed collision. This is more than you bargained for in our time together, but I'm going to tell you.
No,
okay, you ready?
Perfect.
The argument for the longest time that the craters on the moon were calderas from volcanoes and not asteroid impacts. The geologists argue strenuously these can't be asteroid impacts. They've got to be calderas, these 1,000 craters on the moon. Well, why? Because everyone is a perfect circle. And if asteroids are coming from space, they would come from all angles. And if you come in at a shallow angle, you get an oval. And even shallower would be more ovals. So you'd have a whole range of circles and ovals and ellipses. And you don't see that. They must be calderas. It was not
Explain
until...
a caldera. It's a volcano.
Oh, just a volcanic...
and it leads a crater.
Volcanic crater. That's all
like
it is.
Yellowstone.
Yeah. It's a volcanic crater. That's all. And it's a little more poetic, a caldera, you know, but it's a crater left by a volcano that has exploded.
Like the boom was so big, the mountain's gone, and now it's just a big hole.
Or at the top of the mountain, there's a crater at the top of the mountain, like Crater Lake. That's a round hole in the top of a mountain. Was that once a volcano? I don't know, but it's a hole. Okay, so in the 1970s, we were able to do calculations with high-speed computers, with good computers, and what we found was, if the object is moving faster, if the kinetic energy of the object is higher than the energy that's holding the thing together. Ooh. Okay? So what's holding together a rock? The chemical connections of the silicon and the oxygen and everything, and the iron, everything that's making the rock, that's holding it together. You can calculate how much energy is holding it together.
And if it's going 45,000 miles
so
an hour.
write down that number. Now I send in the asteroid with a kinetic energy higher than the energy that's holding it together. On impact, it explodes. Because all that energy goes back into the rock because the thing isn't moving anymore. Where did the kinetic energy go? It digs a crater, number one, by virtue of putting all that energy back into the stone, and that explodes it. So on impact, even at an angle, it is a singular point explosion. And that's why every single crater is a perfect circle. We call that a high-speed impact, where the speed is greater, the energy of the speed is greater than the energy that's holding it together.
That's amazing.
Now, you have experience in this, okay? Have you ever thrown do this next, we're in California, sorry.
Snowballs?
Snowballs. Take a snowball.
Go to Big Bear. They have
Take a
snowballs
snowball
up there.
and face a barn wall and throw the snowball at it, and it'll make a little circular mark on it. Now change your angle to the wall and throw the snowball again. It'll still make a small round mark, and it'll keep doing it. You know why? Because the speed with which you threw the snowball, that energy is greater than the energy that's holding the snowball together. Because hardly any energy is holding the snowball together. It's just loosely packed snow. So when you do it against the wall, you see the snowball completely disappear in a mini snowball explosion, if you will. So this works for any comparison of projectile speed and what we call the binding energy of the object itself. This is why the intercontinental ballistic missiles never carried conventional warheads, because their speed coming out of space, because they leave the atmosphere, go from one continent to the other, and then they fall out of the sky. That speed gives them more kinetic energy than any conventional warhead would have had.
Whoa.
But then we figured out how to make small nuclear warheads. The nukes. Now you're talking energy. The kinetic energy of the ICBM is not higher than the nuclear warhead that we now put in. That's why all ICBMs are nukes.
Wow.